try now.
Can you hear me now out there in Zoom land? We'll keep cutting off the sign.
Oh, yeah. Window to get the interface forward.
Okay, he's good.
So how do I do that?
Move the mouse off to the side. Yeah, and leave.
Oh,
There
all
we
right. Okay.
Okay. So yes, perhaps the bare minimum that we, the robot motion planners, should hope for is to be able to understand how complicated this motion planning is. That's, I guess, the objective of the talk. But here are some problems that I would like to think about in various contexts. In the figure, you see some ants running around on a Mobius band without bumping into each other. You might consider, for example, a planar problem where I have a team of robot cleaners, Roombas or something, that are going to come clean the floor here every night. And maybe there are various possibilities. This table might be gone, so the floor might be empty. Or the table is sitting there, but it never moves. Or during the day, maybe one of the speakers takes one of the tables and pulls it away, so the obstacles for the robots can change from day to day. An analogous problem in space is maybe you have a team of drones that are mapping some, I don't know, taking pictures of some region from space. And you might be in the situation where the airspace in which they maneuver is empty. Or maybe there are some balloons that are fixed that could get in their way, or maybe the balloons could move around day by day, causing the drones to have to move in different ways on different days. All right, so we will come back to these at some point. By configuration space, I will mean broadly a topological space which encodes all possible states or configurations in a mechanical system. I will assume throughout that these configuration spaces are finite CW complexes, at least up to homotopy, and they're path connected. And I'll abbreviate dimension of X as the dimension for the dimension of the configuration space as a CW complex. In this picture you see up here, maybe if the robot arm is only allowed to move in the plane and nothing gets in its way, each joint has a circle's worth of positions in which it could be. So the configuration space of that arm would be a torus. That's one process. So here's the motion planning problem, slightly formally, I guess. We'd like to find an algorithm which, given an initial state of your system and a terminal state of your system, produces a continuous motion of the system from the initial state to the terminal state. In other words, given 2 points in the configuration space, you'd like to make a continuous path from point A, the initial point, to point B, the terminal point. So these considerations showed up in Professor Carlson's talk yesterday, but the perspective is slightly different, as I think you'll see as we go along. Sometimes producing this path is very easy. For instance, if you have one robot or one soccer or football player, depending on what part of the world you come from, and this player is moving around on a completely empty playing field, and you start near your own goal and you want to end up near the opponent's goal, well, you can just move in a straight line from your initial point to your terminal point. And this is nice in the sense that if the initial and or terminal positions wiggle a little bit, the corresponding line segment you make will wiggle analogously. In other words, I can continuously plan the motion on the football field. This gets more interesting if the configuration space has interesting topology. So for instance, if you are now sailing in the ocean and you would very much like to avoid the dragon, maybe if you're to the, I guess that's the northeast of the dragon, you would like to go from A to B in a counterclockwise way. But if you're southwest of the dragon, say, maybe it would be more efficient to traverse from A to A prime, I guess, to be counterclockwise. The issue here is, what if A prime gets closer and closer and closer to A? On the one hand, you'd like to go counterclockwise. On the other hand, you'd like to go clockwise if you're thinking about being close to A. And you cannot rectify this continuously throughout the ocean minus the dragon, which must be avoided. Okay, let's formalize a bit. Xi is the space of free paths on X. There is a natural map from X to the I to the product space X cross X. You give me a path, I find its two endpoints. That's the vibration. The motion planning problem in this context is to find a continuous map, if you can, S, that goes in the other direction from X cross X to the path space, which is what's called a section of this projection map pi. I want pi composed with S to be the identity map on X cross X. And as we were just discussing, it would be nice if this S could be continuous, and it is pretty easy to show that that is almost always impossible. The only time you can make what you might call a globally continuous motion planner S is when your configuration space is contractible. So that leads to the following definition. We'll say the topological complexity of a path-connected space X is the smallest number, TC of X, red K, so that you can cover X cross X with open sets. And on each open set, you can produce a continuous section of this path space endpoint map pi. If you're able to produce such a cover with corresponding sections, you have solved the motion planning problem. Somebody gives you an initial terminal point pair in your configuration space. You can figure out which of these open sets UI is smallest containing that pair, and then use the corresponding motion planning rule for that particular UI. I didn't put it on the page, but you can see the potential discontinuity here. This point AB might be in several of the open sets UI. And one way of thinking about topological complexity, which I won't go into any detail about, is how many of the UIs contain a given X. What's the degree of instability or discontinuity or something. Two very small examples to get rolling. The first one is the soccer field example. If your configuration space is a Euclidean space, you can motion plan using line segments globally. So it takes one open set to cover Rn cross Rn, so the topological complexity is 0. For the circle, things are slightly more interesting. Here you can cover the circle with, on the one hand, pairs of points that are not antipodal, On the other hand, pairs of points that are distinct. If the points are not antipodal, there's a unique shortest geodesic path. You can take that one. That's how you plan the motion on, I guess, U0. And if y is different from x, I'll just go counterclockwise from x to y. So that says the topological complexity of the circle is at most 1. And we know the circle is not contractible, so it's precisely 1. So I wanted to go through quickly some properties of this notion, which maybe some of you have seen before, for instance, at this conference or previous iterations of this conference, just to warm up for the parameterized version we will pursue. So I guess the first point to be made is that the topological complexity of a topological space is, I wrote it barehanded on the last page, it's the so-called sectional category or Schwartz genus of this path space vibration. With that observation, a number of these properties that I've written down become fairly straightforward. For instance, if x and y have the same homotopy type, their topological complexities will agree. You get bounds on the topological complexity from, well, maybe first the LS category of the topological space, or more precisely of the product space x cross x. And then in terms of the dimension of x, and I just wrote down the one in terms of the dimension, there is a product inequality for topological complexity as indicated, and a cohomological lower bound, which comes from something called the zero divisor cup length. This is the cup length of the kernel of the cup product map that Professor Carlson reminded us about last day. So take your favorite field coefficients and think about the cup product map from x, the cohomology of x tensor itself to that of x. This map has some kernel called zero divisors, and you want to look at the largest length of a word you can make with elements in that kernel. In other words, you take positive dimensional homogeneous elements A1 through A, say Q, that are in the kernel of this map, and ask if their product can be non-zero. With just this machinery, well, and a little bit more, we can compute the topological complexity of any orientable surface. The case of the two-sphere is a little bit interesting. The topological complexity is 2. A way to see this is you can cover the two-sphere, cross the two-sphere with 3 open sets. And I gave some little hints about how you might do this. For instance, if your points on the two-sphere are not antipodal, you can again play the shortest path game. If they are antipodal, you have some issues that you have to contend with. One of them can be resolved by the hairy ball theorem. So fix your favorite point on the two-sphere, right, like this one. And then we know that since I've got a hole up here, I can comb all the rest of the hairs on my head. So I can make a non-zero tangent vector field on my head on the two-sphere minus a point. And then you can use that and maybe some stereographic projection and some other fiddling around to make precisely 3 open sets with congenial sections on each one. And I'll leave it for you to play with if you're so inclined. You can't physically do it though. I'm busy at the moment. For other orientable surfaces, things are fairly straightforward. For instance, for the torus, we have this product inequality that I just mentioned, which in light of the calculation for the circle we did a few minutes ago says the complexity of the torus is at most 2. For a higher genus orientable surface, the dimensional inequality tells us that the complexity is at most 4. And then in all 3 cases, again, I will leave it to cohomological fans to check that this cohomological lower bound gives you equality in each and every case. On to non-orientable surfaces. So I gave a related talk to a pretty broad audience consisting largely of computer scientists and a smattering of engineers about this roughly a week ago. And I think this was their favorite part. Non-orientable surfaces. First, here is RP2, the space of lines through the origin in R3. So playing the role of the lines is the red lightsaber you see. Playing the role of the origin is this villain's hand, which maybe you don't see at this instant. I don't know if this will work, but I have to try. And I can't read that, so I don't know. Pardon me? The first one. Oops. What do you mean the first one? Left or? This is probably,
It's asking, the window is asking for permission to connect to your server.
okay. This one leftmost or rightmost?
Left.
That's my left. Yeah. Okay. All right. So there he is. Oh, you can't see it up there. Shoot. All right. This is probably a waste of time. I apologize. Can you share that for a second? Let's try. So you're going to see that this villain is very adept at motion planning. There he is. Okay, thank you very much. Right. So what he intrinsically knows is it takes, I believe, 4 open sets to figure out how to completely motion plan in the space of lines through the origin. Thank you. In other words, the topological complexity of the projective plane is 3. And I gave you a little roadmap to figure out these open sets, which the villain already knows somehow. So the first open set consists of all lines that make an acute angle in the plane they span, and you can just move one line to the other through that angle. The second one, for example, look at all those pairs of lines whose images in the XY plane span the plane. And then you have a preferred direction from the image of line A to the image of line B in the plane. You can lift it up to 3 space. And the other 2 are defined analogously. Okay. Yeah, this is a particular case of a pretty famous theorem of Farber, Tabashnikov, and Yuzvinsky that says for most values of n, this number, the topological complexity of projective n space, is equal to the immersion dimension of that space. And that's why I put the little dangerous curve sign. This is a very hard problem in algebra. To finish the non-orientable surface story, I'll just mention some results of Brunishnikov and Lucille Vanderbroek and I that eventually conspire to show that for higher genus non-orientable surfaces, the topological complexity is as big as it can be. In particular, the complexity of the Klein ball is 4. And I believe that Lucille spoke about this last bit the last time this meeting. Okay, here are our collision-free motion planning problems, at least the first couple. So I will model them with the floor is R2, the airspace is R3, the robots, the robot cleaners or the drones are represented by points. The furniture, the table legs, or the weather balloons are also represented by points. The robot points are Z's, the obstacle points are O's. And we very much want the robots to not bump into each other, to not bump into the obstacles, and we'll assume that obstacles don't coalesce either. So when you want to plan motion in situations like this, non-colliding motion, you are led naturally to study the configuration space of n tuples of points in your ambient topological space, which I call Y for some reason. So this is all n tuples of points, no two of which are equal. And you'd like to study the topological complexity of this configuration space. In a number of instances, this has been done. I'll just tell you some results. If the floor is empty or the airspace is empty, we are trying to study the topological complexity of configurations in R2 or R3. This was computed by Farber and Yudzinski almost 20 years ago. And there are the numbers you get. Just off twice the number of robots. If you have fixed obstacles, then the ambient space that you're working in is slightly different. It's not R2, for instance, anymore. It's R2 minus the positions of the fixed obstacles, or R3 minus those positions. And the topological complexity of configurations in that space is known as well. Farber, Grant, and Yudzinski a little while later. And again, you get similar flavored answers. It's roughly twice the number of robots, depending a little bit on M, but not very much. So the point being, a point being is that this number, which dictates how complicated it is to move in, well, I guess I'll focus on this one, in this fixed obstacle configuration space. It doesn't really see the obstacle. Before we go to the third problem that I posed, I wanted to make a slight detour and talk briefly about a very recent result on configuration spaces of graphs. So a graph will be simply a path-connected one-dimensional CW complex. It's easy to compute the topological complexity of a graph or of configurations of one robot in a graph. You get one if the graph is a tree, which is retractable. You get two if you have one cycle. So this is essentially the circle or the dragon's calculation that we were talking about earlier. And if you have more than one cycle, you have topological complexity 3. Call a vertex essential if its degree is at least 3, and M of gamma will be the number of essential vertices in the graph. The rest of this page, I will largely assume that this number of essential vertices is at least 2. So in 2005, Farber studied the topological complexity of the configuration space of ordered points on a graph. And he was able to carry out the calculation for trees. And when the number of robots moving around on the network or on the graph is sufficiently large, is bigger than twice this number of essential vertices, he found that the topological complexity of the configuration space is as big as possible, twice this number of essential vertices. And emboldened by this, he conjectured that this was always true for any graph, not just a tree. This was shown for various types of graphs in the fairly recent past. And then in the very recent past, last month, Ben Knudsen proved the conjecture in complete generality. So if you have any graph with at least 2 essential vertices, and you have, relatively speaking, a large number of robot agents moving on the graph, more than twice the number of essential vertices, then the complexity of the configuration space is twice this number of essential vertices, which is the dimension, twice the dimension of the configuration space. This number might ring some bells if you read the Nick Scoville talk. There are some similarities which maybe I don't understand and won't pursue. Okay, back to the matter at hand. So now I want to consider the situation where we're studying collision-free motion in the presence of obstacles, but we do not a priori know where the obstacles are. So whatever motion planning algorithms we were to produce here, they should be flexible so as to be able to deal with, you know, the tables are in this position or the tables are in a slightly different position. These kinds of considerations suggest not studying the configuration space of points in Y or points in Y with a fixed number of points removed. They suggest studying the Fidel-Neuwirth vibration or bundle of configuration spaces, where you have a large number of configurations of distinct robots together with the distinct obstacles, and you project onto the configurations that are encoding the distinct obstacles. So I'm going to try to formalize this a little bit. I'll call B the configuration space of obstacles or balloons or cable legs, whatever it is. E will be the configuration space of all robots together with all obstacles. And this projection map that I just mentioned is a bundle or a vibration is robots together with obstacles, just forget the robots. So the way we want to motion plan in this context is if we have two configurations where the obstacles are the same. So the weather balloons on a given day are in a fixed position. I would like to move the robots, the Z's, from the initial configuration to the terminal one. So I'd like to output a continuous motion where the Z's move and the balloons or the obstacles stay fixed. That starts at the initial point Z and terminates at the endpoint Z prime. And a point is that the position of the obstacles are now part of the problem. In other words, what we want to do is the instant we know where the obstacles are, we want to motion plan in the fiber of that particular obstacle, which is itself a configuration space. It's the configurations of all n robots in, for instance, the plane, or that should be a Y, I guess, should be R2 or R3. The plane minus the position of the obstacles on that given day. Here's how this can be formalized. In general, we have a vibration, and I'll assume that the achievable configurations of the fibers are all path connected and non-empty. The base of the vibration I will view as the parameter space of all possible constraints. So that's where the obstacles live. And the fiber over some point B is the configurations that are achievable given the constraints encoded by B. The motion planning problem in this parameterized setting is give me 2 points that live in the space where the constraints are the same. I'd like to produce a motion from the initial point to the terminal point, staying within that same fiber. So my path should respect the constraints given by B as well. The way we can get our hands on that is we make this E cross E over B space, all pairs of points in E who project to the same constraints in B. And then we restrict our attention to paths from the interval to E who project to that same point. This projection is a constant path. We still have an associated endpoint map, which is vibration. So if you give me a path that is in a single fiber, and I project the path, well, I just get a single point. So I can map that path to its initial point and terminal point in E cross E over B. And then we define the parameterized topological complexity to be the smallest number k, much as before, so that you can cover now this whole space E cross E over B with opens. And this endpoint map has a continuous section on each one of these opens. So we'll spend some time with some properties and features of this notion in a minute. And let me tell you some results first. In the case where we're looking at Roombas or robot cleaners on the floor, the topological complexity of this Będlewo vibration involving n robots and m obstacles is this number, twice the number of robots plus the number of obstacles. It turns out -2. When we're trying to parameterize motion plan our drones in space with m weather balloons in the way, the parameterized topological complexity of the Będlewo vibration configurations of m plus n points in space to m points in space is a little bit bigger, 2n plus m minus 1. And I see some typos there. So just look at the formulas, not the words. There are competing notions of topological complexity, or more generally sectional category, depending on whether you like the sectional category of something trivial to be 0 or 1. And the words are dealing with one case and the formulas with another. Sorry about that. Some comments about this. The same results hold for R even and R odd. So for instance, the complexity of configurations of some number of points in R6 mapping to a smaller number of points in R6 is going to be given by the same point. The fiber of these Będlewo bundles, as I think I mentioned briefly, is the configuration space of m robots in the complement of the daily obstacle position. And from a few pages back, Farber, Grant, and Uzminski computed the topological complexity of that space, and it's roughly twice n. But a point being is that the parameterized complexity can be significantly bigger than the complexity of just the fiber. Okay. So here are some properties. Again, this is an example of a categorical invariant. It's the sectional category of this path space vibration that I mentioned. An easy feature is that if you have a trivial vibration, the topological complexity is the same as the ordinary or classical topological complexity of the fiber. Secondly, if you have two vibrations that are equivalent, then they will have the same parameterized topological complexity, and say fiber-wise homotopy equivalent. Third, there are dimensional upper bounds as given. And one that I didn't mention in the classical case, there is a variant. If you have control on the connectivity of the fiber, you can refine your dimensional upper bound slightly. There is a product inequality, and again, a cohomological lower bound. Now, the ideal that one needs to study is the kernel of the map induced in cohomology by the diagonal map from E to E cross E over E. And these are all relevant in the proofs of the two theorems that I mentioned. And I'll try and show you some tidbits of that. First, I guess a truly classical result. The cohomology of configuration space, points in Euclidean space, was computed long ago by Arnold and by Fred Cohen, who lost it not long ago, and I miss very much. Here is a description. Take, if you like, rational coefficients. So the cohomology ring has generators, which I'll call omega ij's, and the relations that you see. The squares of the omega ij's should vanish, and you get these very famous three-term relations among the generators: omega ij, omega ik, and omega j. Once you know this, well, Carlson reminded us yesterday of the Kunith formula as well. That gives you a very explicit description of the cohomology of the space I'm going to abbreviate by E, configurations of M plus M points. And C is our D, if you like. So you have generators corresponding to the first E, as Arnold and Cohen described, and then generators which I'll call omega primes corresponding to the second E. And the relations are what you guess. You have the relations on the omegas and on the omega primes. From this, it's relatively straightforward to get your hands on the cohomology ring of this E cross E over B space. Just take the cohomology of the product space and wipe out the ideal generated by interactions between obstacle cohomology classes. So I less than J less than M was the number of obstacles. So this is saying that the obstacles are fixed, or remembering that the obstacles are fixed. Once you have your hands on the cohomology of E cross E over B, you can study this map induced by the diagonal. And inside the kernel of the map induced by the diagonal is this ideal generated by homogeneous classes, where you take a robot-robot interaction in the first variable and a robot-robot interaction in the second variable and make their difference. Or a obstacle robot interaction first and second and make their difference. Easy to see that these are all in the kernel of this homomorphism delta star. Hard to see that you can compute the coupling of this subideal. Here's what you get. As I indicated, the calculations are delicate, so I'm going to suppress them. From the general property, this gives us a lower bound on the topological complexity of this Fidel-Neuwirth vibration. In the case of R2, you have a nice, well, first of all, I'd like to identify R2 with the complex line and think about configurations in C instead of in R2. You can, this is a matter of convenience as much as anything else. You can make a nice map that takes a configuration of L distinct points and produces a configuration on the one hand of 2 distinct points and then L minus 2 distinct points that are also distinct from 0 and 1 by this nice formula. This is a homeomorphism. It plays nicely with these forgetful maps that show up in vibrations. As consequences of that, on the one hand, if you look at projection from n robots plus 2 obstacles to just 2 obstacles, you have a homeomorphism. Sorry, this is trivializing this bundle. And that says that the parameterized topological complexity of that vibration is just the topological complexity of the fiber, which is known before. In general, you get an equivalence of bundles. And the second factor in this equivalent product bundle is a trivial bundle. So this vibration contributes nothing to the topological complexity calculation. And it says that the topological complexity of the left-hand vibration is at most the topological complexity of the right-hand vibration, where you ignore the trivial piece. So that reduces the problem to thinking about a smaller number of obstacles at the cost of working in C minus a couple points. You can get easily, though, upper bounds from instead. You can get upper bounds from this latter vibration. And various Morse theoretic considerations tell you the homotopy dimension of these configuration spaces. And if you work this out, you get the exact same number that the the coupling calculation gave us last slide. So that's how you deal with the case of motion in the plane. Oops, I apologize. Briefly, for motions in space or in higher dimensions, higher even dimensions, the spatial problem is easy. That's on the bottom here. You can get a quick dimensional upper bound, essentially from considerations that we've already discussed, plus one more observation. Namely, the fibers of the Fidel-Neuwirth bundle, we know their dimensions. And when D is relatively large, you have some connectivity that you can play with. These two observations, together with the dimensional upper bound I recorded earlier, give you the exact same number as the cohomological calculations, which are now long since gone. The higher even dimensional case is a bit more subtle. It uses some obstruction theory and the fact that we understand the cohomology ring of configuration spaces up to rescaling or grading. The obstruction theory is an old result of Schwartz, which says that a vibration has sectional category at most R-1, if and only if it's R-fold fiberwise joined. So this parameterized topological complexity is at most R-1 if and only if the R-fold join that I wrote down in this section, this is actually fairly accessible given what we know about the cohomology rings and the underlying obstruction ring. Okay, let's see. So this parameterized topological complexity notion has been extended in a very number of ways, which I wanted to mention. First, last year, Garcia Calcines Studied and defined what he called the fiberwise topological complexity of a fiberwise space. So for a map P from E to B, he defines the fiberwise topological complexity to be the fiberwise sectional category of the same path fibration that I was talking about earlier. When the input is itself a vibration, this is the same as the idea that I've been discussing. A point here is that he's extended this notion to maps that need not be vibration. So you might think about it, maybe you want a motion plan on a hot plate, and there are some water droplets that bounce around on the hot plate. Well, they might coalesce. So the number of obstacles might change. And maybe the machinery that he's developed here can make some sense of the complexity in that situation. Secondly, not long ago this year, Michael Farber and Kumar Paul extended the notion of sequential topological complexity to the parameterized setting. So in the absolute or classical setting, sequential motion planning asks that you not go from an initial point to a terminal point, but you go from an initial point to a terminal point, visiting specified states in between. So this leads you to study what's called the Arth topological complexity, where instead of now taking a path to its first point and last point, you take it to R preferred points. And this is the notion that they extend. The idea is natural. They, instead of looking at the twofold product E cross E over B, they look at E cross E cross E cross E all over B. They look at R tuples of points in E, which all project to the same point. And they define the sequential parameterized topological complexity to be the sectional category of that vibration. I put these out of order because I wanted to mention this result of Mark Grant last, and then hopefully pursue it a tiny bit. Mark defined parameterized topological complexity of group epimorphisms to be the sectional category of diagonal homomorphism from your group G into the fibered product G plus G over G. If you realize this surjection of groups by topological spaces, E is a KG1, B is a KQ1, and you need a zero connectivity assumption. This group theoretic notion agrees with the notion that we were discussing earlier. Well, then why bring it up? Mark is able to exhibit the upper and lower bounds group theoretically, as opposed to this coupling calculation that I refuse to tell you about. These group theoretic bounds provide an alternate proof of at least the calculation we talked about for the plane. From the eyes of group theory, what we're thinking about here is the topological complexity of the forgetful homomorphism from a large pure gray group to a small one, where you forget a certain number of strings. Okay, maybe one more in the last couple minutes, which fits nicely with the group theoretic picture that I just brought up and the original planar picture. So it's about what are called orbit configuration spaces. The setup is you have, I'll assume a finite group acting freely on a manifold which has no boundary. And then you can look at what's called the orbit configuration space, where instead of looking at n tuples of points in Y, which is different, now you look at n tuples of points in Y whose gamma orbits are different. So the formula is there. You look at all n tuples with orbit of yi, intersect orbit of yj, empty for I different from j. Quite some time ago in his thesis, Miguel Chico-Tencatell generalized the Fidel-Neuer vibration to this setting. So if you take an orbit configuration space with many points and forget some of the points, you have a fibration. The fiber here is now not configurations minus points, it's configurations minus points. So here's an example. Let the cyclic group Z mod R act on the plane minus the origin by multiplication by root unit. The orbit configuration space that arises is a complement, as again Carlson was talking about last time. It's the complement of the reflecting hyperplanes of a certain complex reflection. In this context, this reflection group is something called the full monomial group. It's the Reith product of the symmetric group and this cyclic group Z mod R. In the case R equals 2, this is simply the type B toxic. Kristen Bibby and I are in the process of studying this kind of thing in the context of hyperplane arrangement. And one of the things that we can prove is the topological complexity of this Chico-Tencatell generalized Fidel-Neuer vibration in this cyclic group acting on C star context is the number you see. Twice the number of robots minus the number of minus 1 plus the number of obstacles. Okay, I think I will stop there. Thank you for listening.
Much. So we have time for a couple of questions.
Some. I was wondering whether the lower bounds for simplicity, like always come from some homological consideration.
The ones that I know do.
Okay.
I did not mention it because it would have taken way too long. The way Lucille and I finally computed the complexity of the fine model was by much more subtle homological considerations than just this, coupling. There are for a given vibration, there are some canonical one-dimensional homology classes, maybe not one, but canonical homology classes that one can study in the context of TC. This class was studied by Costa and Farber, and they proved something of the flavor. The nth power of this class is non-zero if and only if TC of the space is at least something. But this class is in general very hard to do. It's a twisted cohomology class with coefficients in the group ring, the augmentation. Lots of fun to play. Sure.
Yeah. So the parameterized TC approach, we don't have a setting for moving obstacles and so forth, but the obstacles are sort of fixed during the movement of the road.
Yes, yes.
Do you have a setting also for something which the movement would be
Not yet. Right. And that's why maybe I mentioned that these ideas are to some extent complementary to what Carlson was talking about last time. That's what he wants. Right? He wants the obstacles to be able to move along with the robot. All right. Well, so maybe there's one pragmatic comment about that, and that is, well, if the robots and obstacles are all moving, why don't I just treat them as the same? So that reduces to the case of no obstacle. But yeah, your point is still well taken. You want some preferred collection of objects or single object moving in the presence of other things or things that itself
and being his name. So, you know, the real answer to your question, I guess, is I don't have that knowledge. I might be able to cheat my way out.
All right, so let's thank our speaker again.
Thank you.
Thank you for your help.
Teraz ja mam na tym razie. Będzie można kliknąć na stronę, to jest problem. To może postaram się nie klikać. Czy mogę korzystać z tej myszki, czy to będę chciał skorzystać z tego wskaźnika? Znaczy te duży ten trójkącik się może to zmniejszyć. Znaczy nie, ewentualnie z tego. Tutaj jest, na tym ekranie. Jest. Dobrze. Okay. To będzie z tego korzystał?
Przepraszam za to gdzieś utknęło, ja prześledziłem tam korespondencję tego blogu, na stronę, ale wszyscy są teraz na łopach, nie wydarzy do Także poszło tak jak wstało. Nie, to się nie, przepraszam, doktorowe. Czy było na przykład doktorowe, miało być przerobione na doktorowe środowiska. Ja above my pay grade. Zaczniemy 5 po, dobra? Bo Piotrek, nikt nie miał postać.